This is an Agilent U3402A, 5.5 digit DMM. Guess it's targeted more at the educational market, so it's not quite as fancy and high-end. You know, they make a 6.5 digit kind of in the same form factor. I guess this is a newer model as well, but for the price, I think I paid $150 for it. It is marked as does not power on, so I expect to run into some problems there, but I'm hoping I can repair it. It's a bit of a gamble, but it seems like it's a possibly reasonable gamble, because if it doesn't turn on at all, maybe it's something very obvious, like blown fuse, power supplies, that kind of stuff. Versus if it does turn on but acts funny, that could be pretty hairy to solve, and you know, maybe it's possible, but probably not worth the time. So you're going to watch me do this somewhat live. Hopefully we'll get some good results out of it. So a couple of things to note about this. It's in really, really good physical condition. In fact, the little protective film on the display is still on it. I don't really see any other major damage, but I did notice a couple of things here, which may be some kind of clues. The fuse holder, which is really the fuse for the current measurement, definitely looks like somebody attacked it with an inappropriate screwdriver, and I have a feeling that was probably the eBay vendor frantically trying to get it to work to see if they were going to be able to get more money for this thing. Likewise, if you look around in the back, which overall looks pretty good, I can actually see a few markings here on the power inlet, which look like somebody's been prying around there with a screwdriver. Most likely just trying something simple like replacing a fuse. So I kind of expect it's not going to be that obvious, but we'll find out. Some more clues. This thing actually came with a lot of the original packaging. The original foam end pieces were in the box. The original probe package is still in the box. And this looks like it's complete and practically like it's never been opened before. I just recently bought an Agilent multimeter at work, and it came with a package very similar to this. These aren't quite the nice ones where the cables disconnect from the probes, but it's got a lot of the other nifty stuff in there that's useful, so I don't know, this looks awfully new. I'm curious to figure out what the story is with it. But first things first, let's see if it behaves as claimed. Plug some power in. Make sure it's off. IEC is plugged into the back. And let's see what it does. Well, I guess it is as advertised. Does not turn on. So let's get in a bit to the investigation. First things first, I'm going to unplug that. But I am going to try to pop this fuse holder out and see what we find. Just grabbing an appropriately small screwdriver here. It's a little too big. There we go. Alrighty. Well, the fuse looks intact. This is a 400 milliamp, 250 volt. This holder looks like it may also set the line voltage. It currently says 120, which is fine for the US. I will use my cheap and cheerful but still halfway decent little X-Tech multimeter here to do a continuity test on the fuse. Alright. Rear panel fuse looks good. So to pop this apart, looks like I'm going to need to dig up, I'm not sure exactly what size Torx that is, maybe a T15. So I'm going to go dig up, oh wait, I actually have one sitting right here on the bench. It's a T15. Well, that's pretty fortunate. Turns out these RT15s are something very close to it right on the back panel here. So those look like they're captive. It's a nice little assembly the way that pops off. The rubber guard. Very well built, typical of Agilent stuff. There's embedded brass inserts for taking machine screws of some kind on the back panel. It's well made. I'm guessing this handle assembly needs to come off, and well, that's certainly quite a bit easier than it is on some oscilloscopes. Just basically outward force and lift up. So it's still not coming off. There's another screw here on the bottom. This looks like another Torx. So set that aside. And there we go. Now the back panel is free, or rather the enclosure is free. This is measurement and control board. This is the front panel board up here. Transformer. Probably the power supply board, though there's a serial port on the back of this thing too, an RS-232 port. So I see a transceiver. Actually, there's a couple of opto isolators. Just looking for any obvious signs of scorching or damage or anything like that, and I don't see anything obvious. I would expect to see anything like that initially in the power supply section. Transformer primary connects to the IEC connector, but there are also a couple of lines that go through this little, I don't know, firewall, for lack of a better term here, onto the main board, just as to the age of the instrument. I see an 1139 code in here, so this is probably 39th week of 2011. So this is a very recent instrument. So here's another look. This is the underside of the main board. Now I start to understand why those lines from the transformer go onto the main board. The front panel switch, sort of in the classic style, is a really long actuator that goes to the back corner of this main board, and that's actually where the power switch is. It's interesting they would take it that far back and put it there and not have it be part of the power supply board, but the power supply board wouldn't necessarily need to have any AC on it normally either, so I guess this is as good a choice as any. I just am surprised they would make that choice for noise reasons and other considerations like that, but they know what they're doing. So, but this chip right down in here actually has an Escort name on it, and I don't really know much of the lineage of this particular line of multimeter, but I believe Escort is a test equipment company that Agilent bought, or they at least got this line. I think I read that someplace. So this is really probably not an original Agilent design and has been adapted from another company. So from tracing the wires out, you can see that coming straight off the IEC input, they connect over to this main board on this little 2-pin connector. I don't see any switches in between, so if any time that is plugged in, there should always be AC voltage here. In fact, there is. I see 120 volts. Probably kind of hard to see there with the glare. There we go. So that's all well and good. Not really testing very much there, though. Like I said before, the switch is located on this, so the only two things I see coming back off of it are these other two. There's a red and a blue. The switch is currently off, so I see no voltage. Flip the switch on, 120 volts. So the switch seems to be doing its thing. And what I'm trying to do is trace out this pair that comes off of the main board. And from what I can see, this blue wire looks like it probably goes into the transformer as one of the primaries. This red wire goes back into this fuse monstrosity over here. Looks like it goes into the center of that, there are quite a number of things that come off of it. It's hard to determine exactly what's going on with that. There are two more wires that come off of that go back into what I'm guessing is the primary side of that thing. Now, it might be easier just to get a sense for what's going on here if I try to disconnect this off the power supply board and actually take the transformer out. Now I've got both of those out. I can lift the transformer up, at least within the bounds of its cabling, and indeed there's a whole bunch of stuff, most of that stuff in fact. Now one thing that occurs to me is that this is a 120/240/100/220 of all kinds of voltage arrangements, and this is not an auto switching setup. It's not a universal input like some devices are, and I believe you put in a different blade into this thing to set the different voltages, so these are probably different primary windings. I don't know exactly how that's handled, but clearly this blue wire, which goes back to the main board, is the common one. And I guess there are 1, 2, 3, 4. There are 4 different voltage settings from 100 to 240. So the blue wire is the common one, and then it's 1, 2, 3, 4. So I guess you would put in a different module, or maybe there's a way to change this module to apply different voltages to it. Really trying to unwind what's going on with all of this business coming off of the fuse block here. So this red line that comes back from the main board connects here in the center, and then the 4 different primary taps are sort of arrayed around that. So again, here's the little fuse cartridge. Once you take it apart, this little insert you just turn 100 volts, 240 volts, 220 volts, and when you pop it in, it just places this little brushed contact on the correct side. But this gives me a clue as to which of the wires inside of here are the ones that I care about, and I have a strong feeling they are really just literally in the correct physical positions. So that looks like, since the tab here is on the right, I have a feeling then that this red wire is my 120 volt primary. And I'm going to test that out by putting this back in. I will power this up with nothing connected to the secondary of the transformer. And there's my multimeter complaining. So click, I've turned it back on. I'm going to put one probe on the blue, which we've determined is the common between these two. And we know that red gives us 120 volts coming off the main board. Red goes to the center of this fuse thing. And I'm guessing, yep, that side that I expected was the 120 volt output of this thing is giving me 120 volts. So the fuse is good, the holder is good, everything is good going into the transformer. The next question I have is, well, is one of the windings on the transformer toast? And we can find that out. I'm going to take a few notes here and write down the placement of all these so I can pull this apart. So here I've got the transformer pulled out. This blue line with this little white connector on it is the common line that goes back to that main board. I'm just going to stick a scope or a meter probe in there and just see if I can see any resistance at all to any of these other windings. Not looking so good. kind of looking like this common winding may be blown. I think this one is common. And I think this is 120 volt. So, going to start off the known one here and see what orange to red gives us for resistance. So quite low. I see, I don't know, 5.4 ohms. And then red to brown, which is to the next adjacent on the other side. So I see 74 ohms. And then I'm going to try red to yellow, which appears to be the last tab. See 90 ohms to that one. Now I have a hunch these are actually in the correct tap order for the different voltages that this thing supports. I have a feeling that was common. I have a feeling that orange is 100 volts even. Red was the 120. Brown is the 220. And yellow is the 240. It's my guess anyway, and the ratios of the resistances kind of bear that out. So this is what I've determined by studying the little voltage selector. And we can compare it to what I was writing out here before. So I am still quite confident that blue is the common. I determined that orange was the 100 volt. The red was the 120 volt, as we thought. The brown is 220. And yellow is 240. So that is in order. That is exactly how these things come off the transformer. And it does match the resistances that we measured, at least in terms of ratios. 120 to 100 volts is a very small resistance. They would be pretty close together in terms of where those taps fall. 120 to 220 is fairly large, but 220 to 240, it's only like 16 ohms difference. So I think it all lines up, it all makes perfect sense. Now, why does any of this matter? Well, I looked on the Agilent website, and they do not seem to offer this transformer as an orderable part. And that really kind of sucks, because this is obviously a custom transformer for this particular instrument. And if they don't sell it, I'm not likely to find it anyplace else. The way that this thing was originally intended to work, the blue again was the common. We're in North America here, 120 volts. We're using the blue and the red. Well, the instrument is designed to work all the way up to 240 volts for some other part of the world. Well, the interesting thing to consider is that the relative size of the relative number of windings between blue and red for 120 volts should be the same as from the red to the yellow, which is another 120 volts basically. So to go to blue-yellow, it's 240. So if I rewire this thing a bit, let's say someplace between where the blue wire goes into this transformer and the first winding, the orange one, it's broken for whatever reason. Who knows? Maybe it got fried. Maybe it mechanically broke. Who knows? But my theory is that since I'm only going to ever use this thing here in North America, what I can do is repurpose it a bit and use the red and the yellow and basically have the same ratio on the input. But I can pull the yellow and I can actually just reroute this onto the main board, and that might give me the voltage output that I need. It seems logical to me. It's measuring reasonably across there, so I guess it's worth a shot, and we'll see if it blows up or not. Alright, so I'm just about ready to give this thing a try. I've left the secondary connections disconnected from the rest of the meter for the moment. I've got the presumably broken common wire kind of sitting here floating. And what I've done is I've threaded the yellow wire, which if you remember is the 240 volt. I'm now basically treating this yellow wire as the new common, being that it's the other side of the transformer. I've got that sort of temporarily pressed onto the post up here where the blue wire used to be connected, so that when I flip the switch, it's basically going to put 120 volts across red and yellow instead of the old blue and red. And I want to make sure it doesn't blow up or go wildly out of control with the meter connected, so I'm going to do my first test. Power is off, plugged it in, I put the fuse back in. I've got everything pretty much wired up the same way as before, except I pulled off the yellow because I'm using it elsewhere. And this is just to make sure the fuse doesn't blow and any other thing horrible doesn't happen. So here we go. And nothing terrible seems to have happened. Can't really hear much. Don't know if the fuse blew, but I think I'm going to just shoot the moon here. Plug these back in and give it a go. Let's see if maybe we'll get lucky. Look at that. Powered right up. So somehow that transformer got damaged. I don't know exactly how. Like I said, I didn't see any markings on it that looked like it got scorched, but you know, those are really, really thin wires, so it could have, something easily could have blown those wires off. But would that really have happened without blowing the fuse first? I don't know. Is it just a manufacturing error? But I think this is a pretty clever fix that you may be able to use in some circumstances. Like I said, I can't find this transformer on the Agilent part site. They're very good about a lot of parts, but if it's not on there, I don't know how easy it is to get, if you can get it at all. So I'm pretty happy for $150. I just managed to score myself what looks like a brand new Agilent bench DMM, and that's pretty awesome. So I'm going to try to clean this fix up a little bit and put things back together, and we'll look into the meter a little bit once I get that done. So I've got this thing basically buttoned back up. Ultimately, I decided that it was probably a good idea to disconnect the other voltage selects because they're no longer valid in this configuration. If somebody did switch it over to 220 or one of those other settings and plug it in, potentially really bad things would happen. So I clipped the blue wire, which was the common, and stuck some heat shrink on the end of that. And all I did was take the little connector here that goes back to that main board, and I just spliced it onto the yellow wire, which is the repurposed common. Got that all packaged back up. Plug the meter back in. And we can see that power's up just fine. pretty nice there in my now growing little stack of Agilent gear. Turn it on, comes up. Hook up some probes to it. We'll do a voltage measurement just as an experiment. I've got my Agilent supply set at 3.3 volts. Apparently not quite 3.3 volts. Alright, that's pretty cool. Seems to be functioning for that anyway. Let's crank this thing up to its max. 8.58, 8.59. Seem to agree reasonably well across a couple of points anyway. Got it's a 12 volt, I don't know, it's like a 10 watt 12 volt lamp. Turn this up to its, we'll put 8 volts into it. 8 volts, 1.27 amps. So it's got a milliamp mode, which is up to 1.25 amps, and then a high current mode, which is up to 12 amps. So let me get these wires sorted out a little bit here. I've got it set on the 12 amp range. Sure enough, it passes current just fine. The light's lighting up, as you would expect. But the meter isn't showing anything, and this baffled me for a minute. But it turns out that, for whatever reason, on the high current mode, auto ranging does not function. It's just not the way the meter works. So you have to manually select the range. So just hit up a couple of times until it says amps, and there you go. It's reading 1.2638 amps. And that reasonably well agrees with what the power supply thinks it's putting out. Now, supposedly we can do a dual measurement with this, and I don't think this will be a great example of the best way to use it, but plug a probe into the voltage side, and if I do second, it's a second, and then you pick the measurement, so let's say DC volts, and it starts clicking like there's a turn signal on, which I think is pretty funny. What I really expect it's doing is it's literally taking one measurement, taking another measurement, taking another measurement, flipping back and forth. Like I said, this isn't the most expensive or the most advanced benchtop meter they ever made. But we see in the primary display, still reading current. Secondary, we're reading volts. It's updating pretty slowly. So at that point, it's reading a pretty small voltage drop from the ground to that point. And if I flip it on the other side, we should see the supply voltage, but in negative, minus that drop, I believe. Right, so it's minus 7.8482. Whatever that drop we were reading before is the difference between that and the 8 volts that we're nominally set at. So looking a little bit more at these different measurement rates, you can directly see the trade-off between speed, this is currently in fast mode, and resolution. We're only getting 2 digits after the decimal point. If I put it back into slow mode, you see we get 4 digits after the decimal point, but the response is much slower. It's doing averaging and whatever other algorithms it's doing internally to get that nice stable reading. It's fine for a lot of things, but it's not ideal. And there is a middle rate. This is the middle rate, so we get 3 digits after the decimal. It's a reasonable response, reasonable trade-off. Now where the speed setting really makes a big difference is in the continuity mode. I'm going to go back to the slow mode here. Now this is technically the mode they want you in for doing continuity. It's a 2-wire resistance measurement. with a beep tone. So we're in slow speed. It's a good 400, 500 milliseconds before that triggers. Slower, or it's quicker sometimes, but... So that's pretty darn slow, and I was pretty disappointed the first time I saw that. But you can, in fact, change the rate even in this mode. So now I just put it in medium. It's a little faster. And this is now fast mode. It's considerably better. It still doesn't pass the rapid test. But you can put it into diode test mode, which for, I think, many cases will actually work fine for continuity. And that's actually pretty fast. It's not as fast as having a buzzer directly connected to the probes like continuity works on some meters, but for something that's very obviously measuring what's at the probes and deciding whether that's a continuous circuit or not, it works all right. So yeah, it's minorly inconvenient to have to change the rate, but for those times when you need more precision, changing the rate's not a huge deal, and maybe I'll just leave it in medium mode for most of the time. Another thing to check out is the min-max. So this is currently showing max. I think it's clearly beeping every time it captures a new maximum value and then just holds that for you to look at. Get these out of the way so you can see what the supply is set at. So 5.93, that's what it captured. I can put it in min-max mode. I'm not really sure what that displays. It seems to be just showing the live reading. But if I put it in min, it's showing, I guess, the minimum that it captured during that time. And if I go below that, it beeps to tell me it's capturing new ones. So that's pretty handy. I mean, I think most of my better meters have had that feature on it. Not one I use very often, but this seems to be very easy to use. There is a relative reading mode. So you can take a relative measurement from where you are. So let's say we park this at 5 volts. Take a relative measurement there. And this is just like tearing a scale. Basically, you're saying that's 0. Show me the relative difference from that point that we captured. And then when you want to turn it off and just go back to absolute, just hit it again. So yet another feature that I think a lot of my handhelds have had that I don't use very often, but when you want it, you want it. So it is nice to have it in the Benchtop. And that's about it. I think I'm going to need to dig into the manual a bit more to see what other features this thing has. I definitely see a few things on here that aren't obvious to me. You know, pretty basic meter. Definitely a good deal for the price, and it was a fairly easy fix. The thing's only a couple of years old, if that. You really can find a good deal on eBay, but you got to be really patient about it. If you look on there, there's just a lot of overpriced stuff. And actually, honestly, even this thing was listed at over $400 or $500, and it had a make offer on it. So I made an offer at a what I thought was a lowball price, and the seller took it, and I took the gamble that I'd be able to fix it. Thankfully, I was able to fix it, and got a new tool for the bench. Well, I think that's it. Until next time, take it easy. But the most critical part, this is like my favorite thing to do with any piece of gear. Take that off. Much better.